Good morning, children. We are on to the next lecture on alkenes. In the last video, I have already covered two methods of preparations of alkenes. Okay, so in this video, I will be completing all the methods of preparation of alkenes, that is dehydration of alcohols and dehalogenation. Okay, now first let us consider dehydration of alcohol. Now, alcohols can be dehydrated and what you will get is alkenes. Let's take the example. Suppose I write like this. Some alcohol I have written. I've just written the skeleton, carbon skeleton. And what you want to prepare is a double bond. And dehydration means water is also eliminated. Right? Now, one thing is for sure that it is also following beta elimination. Because you can notice this carbon atom is alpha, it is bearing OH, and the remaining, the next adjacent carbon atom is beta. So from here, there is one H present here. There is one H present here. So H from the beta, OH from the alpha, this will be eliminated as water. And we will be using some dehydrating agent. The common dehydrating agent which we use is concentrated sulfuric acid. And if you are using concentrated sulfuric acid, the temperature has to be higher temperature. It is 443 Kelvin temperature. Right? Now, instead of concentrated sulfuric acid, you can also use another dehydrating agent, that is alumina, Al2O3. If we are using Al2O3, around 623 or 633 Kelvin is required. Right? So this is the main, reaction in which alcohol is converted into alkene. Now let us, specify and write as, say, ethyl alcohol. Ethyl alcohol, if we are writing, ethyl alcohol in the presence of, I am writing now only concentrated sulfuric acid, but I told you it can be even alumina. If this is found, that means this is also dehydrating agent. So you will be using concentrated sulfuric acid and the temperature is higher, 443 Kelvin. So from this, OH will be eliminated, from the beta, H will be eliminated. So what you will get is water. Apart from that, what you are getting is alkene. That is, ethene is obtained. So ethyl alcohol can be converted into ethene in the presence of concentrated sulfuric acid. Now, let's take another, alcohol and see. This is primary. This is primary alcohol. We have taken primary alcohol means the carbon bearing OH is a primary carbon atom. Right. Now, let us take example for secondary alcohol. Say, we take this as OH and this is CH3. The carbon atom bearing OH is a secondary carbon atom. It's a secondary carbon atom. Right. So again, you are carrying out in the presence of concentrated sulfuric acid, 443 Kelvin. If it is lower temperature, it will not give alkene. It will give ether. That we will talk about in ether chapter. So this is the alpha carbon. Alpha carbon will lose OH and beta. Here this and this both are betas and both will give the similar product, so no issues. So we will remove from any one of the beta carbon and what you will get is CH3, CH, now double bond and CH2. Right, because this H is not removed. This is alpha carbon. This one was beta. Even this was beta, it will give the same product. You are getting propene in any case. Whether you take from here or here, you will get the same product. Okay. Now, let us take a secondary alcohol and write CH3, C, OH, CH3 and CH3. We have taken secondary alcohol. We are using same thing, concentrated sulfuric acid, 443 Kelvin. So what will happen is, this is tertiary carbon atom now. This will lose, this is alpha carbon bearing OH. Any one is the same, because it is going to give a similar product. So I'm just showing you from the lower one. So if this is losing H, then CH3, C, CH3, double bond CH2. If you remove from here or here, then also it is not giving a different product. It is the same. What we have taken is, this is from 1 degree, You're getting alkene 2 degree or 3 degree. In all the cases, what you're getting is alkene. Plus, of course, water will be obtained in this. So, what is the name of the product here? It is 2-position methyl. So, 2-methyl propene. So, the name of the product is 2-methyl propene. And this was, of course, propene. And here this is ethene. I hope you are able to write down these names. This was ethyl alcohol. This is isopropyl alcohol. It is isopropyl alcohol. If you want, you can give the IUPAC name also. Propane 2-ol. Propane 2-ol. This is tertiary butyl alcohol. Common name. Common name is tertiary butyl alcohol. If you want, you can give the IUPAC name also. You will select the chain. This will be your main chain. The longest chain. Don't make a mistake of taking this chain. This is the longest chain. At 2 position, numbering any side will be same. 2 position you have methyl, 2 position you have all also. So its name will be 2-methyl, the prefix, word root prop, ane single bonds, propane 2-ol, 2 position pe all you have. Right. So this is 1 degree, this is 2 degree and 3 degree. Now suppose you are asked to compare the order. If you are asked to compare the order of dehydration, means if I am comparing 1 degree, 2 degree, 3 degree alcohols, which one will undergo dehydration to greater extent? It will be like this. 3 degree is maximum, then you have 2 degree and the least is 1 degree. 3 degree, 2 degree, 1 degree. Right? Now, let us take some more examples of dehydration. Now, we are taking another example. This is a secondary alcohol only. But now see what is the difference. This is having 2 different type of beta carbon atoms. This is alpha carbon. This is beta. This is also beta. Alpha carbon will lose OH. And beta has to lose H. Which beta should lose H? This one or this one? So there is a doubt. Wherever there is a doubt, you will have to follow some rule. In organic chemistry, wherever there is a doubt, there is a rule. Now let us see what products you are getting. If you remove from this carbon atom or from this carbon atom. Let me remove from here first. From this beta, if H is removed, then you will get CH3, CH, double bond will come here, because if 2 things are eliminated from the adjacent carbon atom, the single bond becomes double bond and you will get this. And if this beta loses H, now this beta carbon loses H, then you will get CH3, CH2, CH, double bond, CH2. That means in first case you are getting but 2-ene, and in the second case you are getting but 1-ene. Right? So but 1-ene and but 2-ene. Now which one is more stable? In the previous video also I have discussed in dehydrohalogenation that more alkylated alkene is the stable product, because it is more alkylated. Either side you are having methyl group. Here if you isolate the carbon containing double, you have only one side alkyl radical. So you will find that this one is more stable. There are 2 reasons for that. One is more hyperconjugation, you can say, or exactly only one reason, or instead of hyperconjugation you can also say it is more alkylated alkene. So which rule is that? The rule which is applicable here is Sedgwick's rule. Sedgwick's rule or Zetsef's rule. It is one and the same thing. Okay, so you will get this as the major product. It is nearly 80% and this is only 20% form. Right? Now, for this we should be understanding the mechanism of the reaction. Without that, you will not be able to do in case some different type of questions are asked. Okay, now let's first consider the mechanism of dehydration. Now to understand the mechanism, we are taking example of ethyl alcohol. Okay, so actually ethyl alcohol or whatever alcohol we are taking, it's acting as a Lewis base in it. It's acting as a Lewis base. Lewis base means it's an electron pair donor. It is an electron pair donor, or we can say it can accept a proton from the acid. Okay, so what happens is, first step, you have taken sulfuric acid, that's a dehydrating agent. So sulfuric acid will first lose this H plus and it will form HSO4 minus. Right? So this is the first step we are considering. You have ethyl alcohol CH3CH2OH with 2 lone pairs of electron over here. So this H plus which is formed here will attack here. So what will happen is the lone pair of the electron on alcohol is given to this. It is given to this and it will accept the proton. That means alcohol is accepting the proton of the sulfuric acid. This reaction is reversible. So when this accepts the proton, it will form CH3, CH2, you will have O, H, H. One lone pair is given, only one is left over and it will acquire a positive charge. That means the alcohol is protonated now. This is called as protonated alcohol. Yeah, this is clear. This is the first step. Right. Now, in the second step, what happens? In the second step, this protonated alcohol CH3, CH2OH, H, one lone pair and the positive charge is containing oxygen, positive charge on the oxygen. Oxygen is never stable with positive charge. So what will happen? It will pull this bond electrons towards itself and try to get its lone pair back. So when it does this, what will happen is this bond goes away and lone pair is back on oxygen, means oxygen gets both the lone pairs back. It will come out, this bond will break now. It will come out as water. So when this goes away, only this carbocation is left over, because this bond along with the electron has gone towards this. It has formed water. So now it has formed a ethyl carbocation. What is this? It is ethyl carbocation. It has formed ethyl carbocation. Right? This is a slow step. This is a slow step. Right? So this slow step means it is the rate determining step. This is the rate determining step. Then in the third step, what happens? This ethyl carbocation which is formed, it is the ethyl carbocation. Right? Now I'm just writing these hydrogen atoms like this. So in the last step, what happens is the proton is eliminated from it. It loses the proton. How will it lose the proton? There is carbon containing positive. So what happens? One of the bond comes back here so that carbon's positive charge is satisfied, and this bond electrons have gone here, means this H is now free. So this H comes out. It will come out as H plus, and when this has come here, means there is a double bond between the two carbon atoms. This H2 is as such, this H2 is as such, one H has. Where has this H plus gone? This started the reaction. So this H plus is taken up by HSO4 minus and you will get the sulfuric acid back. Right? This reaction is quite fast. It does not define the rate. It doesn't, affect the rate at all. Only this was the rate of the reaction. So the catalyst is generated back. That means in this process, in the mechanism we have studied in dehydration, a carbocation is formed. It's an important thing. You'll remember carbocation is formed because this will help us in deciding the products in some more examples. Fine? Right? Now let's see how we can apply. Suppose we consider this example. This alcohol we have taken, this is butane 1-ol. And we are carrying out its dehydration in the presence of concentrated sulfuric acid at 443 Kelvin. right? Now, what normally we think, this carbon is containing OH, this is alpha, this is beta, so it should be losing OH and beta should be losing H, and what we should be getting is CH3, CH2, CH double bond CH2. That will be our expected product, but it is not correct. It is not correct answer. It is not the correct answer. Why? Now, because you have learned the mechanism, you should be able to think over it. What happened here? This gave sulfuric acid gave H plus. So if I write down here, let me just explain here. Now every time you needn't write the whole steps for predicting the product. What you will do is, you just understand the concept. Okay, this was having lone pair. This H is not there in the beginning. This was the alcohol. Now sulfuric acid has given one H plus to it. Means when this combines with H plus, what will happen? This will get protonated. That is what I was writing. I was just skipping one step. Now let me write only for your better understanding. There will be one H plus. This will be taken up by alcohol, which I just told you in the mechanism. So this lone pair will be given to H. So H will go form a bond. There will be only one lone pair left over. That means the alcohol gets protonated. When alcohol gets protonated, means oxygen getting positive is not okay. This will come. When this comes here, it will come out as water. One water molecule will be formed. And this should get a positive charge. So it gets here, you will get CH3, CH2, CH2, CH2 with the positive charge. Right? This was our thing. This is the primary alcohol. Now, this is such an example where H can shift. There can be hydride shift. From the adjacent carbon atom, that is from this carbon atom, one H will shift this side such that it migrates here and it rearranges itself to more stable carbocation. That means one of the H along with the bond, it comes this side, makes this H3 and the positive charge shifts here. That means this primary carbocation rearranges itself to become more stable 2-degree carbocation. Right? Now, because 2-degree carbocation is more stable, this will be the preferred one. Now, for this, there are again two betas. You can check which beta should lose H, this beta or this beta. This beta, if it is losing, less stable alkene will be formed. If this beta carbon atom loses H, it will form a stable one. That means you will get CH3, CH, double bond CH, CH3 as the correct answer. Very, very important reaction. This one. It's a very, very important application of the mechanism of the dehydration of the alcohol. Though this was primary, right, it was forming 1-degree carbocation. We did not form but1-ene. This was a wrong answer. It will instead form but2-ene as the major product because there is hydride shift. There is hydride shift. This is called as hydride shift. Right, from here, the secondary, second position, this will go shift towards here. This becomes H3 and 1-degree carbocation rearranges itself to form 2-degree carbocation and the but2-ene will be the major product. This is called as 1,2 hydride shift. It is 1,2 hydride shift. Let's take one more example where we can apply this mechanism. Let's take this example. Suppose this is subjected to dehydration in the presence of concentrated sulfuric acid, 443 Kelvin. This is alpha carbon, beta, this beta doesn't have H, this beta has H. So if this beta has H, what we will expect is this side should be losing H and you should be getting a double bond here. But that doesn't happen because we have to check the mechanism for it. Right? So what will happen is, first step, this H will be taken away. This is H, sorry, here. This is not complete, this is H. So one H plus from sulfuric acid will be taken by the OH group. So what you will get is CH3, C, CH3, CH3. This is CH, this is CH3, and you will get that OH2 with only one lone pair and the positive charge. So when this is formed, O will not be happy with it. It will take this lone pair of electron. It will come out as water. So what you expect is you will be getting CH3, C, CH3. This is CH3. You have single bond, CH, CH3, and this carbon getting a positive charge. Now, we expect this beta should lose H, but that doesn't happen. In fact, just on the adjacent carbon atom, if you find a methyl, what will happen? This methyl will shift this side along with this bond, because this is not having any electron, extra electron. In fact, it is having a positive charge. So this methyl, if it has to attach here, it has to come out as CH3 with the electrons. So this will shift here because the present carbocation is 2 degree carbocation. Present carbocation is 2 degree. So there will be methyl shift in it. So this methyl will shift here and it will result in the formation of CH3, C, CH3. You will have CH, this CH3. Now instead of CH3 here, you will write down on this carbon atom. That means this positive charge will be now here. This is 2 degree carbocation. This one is 3 degree carbocation, which is more stable. Now this 3 degree carbocation will undergo deprotonation. One H plus will be lost. So H plus should be lost from where? It can be lost from this beta, because now with respect to this carbon containing positive, this is beta, this is also beta. Which beta will form a stable product? Obviously this one. So this beta will lose H, and the final product form here will be CH3, C, CH3, double bond, C, CH3, and CH3. This will be the major product. That is 2,3-dimethyl butene will be the major product if this one is undergoing dehydration. A very, very important question to understand the concept. Good for your competitive exams. Right? This is dehydration of, alcohols. Now the last method we are taking for the preparation of alkenes, that is dehalogenation. It's a very small method. Comparatively easy. So dehalogenation is mainly from vicinal dihalides. Vicinal dihalide. Now what are vicinal dihalide? Vicinal means when two adjacent carbon atoms are substituted. Dihalides means they are substituted by halogen. This is vicinal dihalide. Suppose we write like that, CH3C and two halogens are present on the same carbon atom. Then this is called a geminal dihalide. But we cannot prepare alkene from this, we can prepare from vicinal dihalide. So reaction is dehalogenation, and otherwise we have to use here dehalogenating agent. You will use zinc as a dehalogenating agent, and you have to heat it in the presence of zinc. So what will happen is this zinc and Br, it will come out as ZnBr2. It will come out as ZnBr2, plus when from the two adjacent carbon atoms you have removed something, two atoms are removed, single bond will change to double bond. So you will get CH2, double bond CH2, that is alkene will be formed. Got it? Now suppose we want to prepare propene, and we have taken CH3, CH, CH2. Here you have Br, you have Br here. It's 1,2-dibromo propane. So you will be using zinc and you will be heating here. So this zinc plus both these Brs will go away as ZnBr2. And you will get here CH3, CH, double bond and CH. That means propene will be obtained. This is preparation of ethene. This is preparation of propene. Okay, so with this video, I have completed all the methods of preparations of alkenes. Okay, please practice these, and in the next video, I will be explaining the chemical properties of alkenes. Thank you.